Hi, I'm Antonio Sala, and in this video we'll model this three-spring system as a set of ordinary differential equations. We'll assume that there is some friction at the wheels of each of the masses in these carts, but we will not assume, for instance, that there is kind of damping due to the relative movement, for simplicity, and our input signal will be the displacement of this right extreme, so someone pushes or pulls in here, and that movement will make this spring stuff vibrate. As we are modeling mechanical systems, the basic equations will be Newton's law, that the time derivative of positions are speeds, and force equal mass times acceleration if we divide by mass. This ends up being that the derivative of the speed, which is the acceleration, is the resulting force in object I, 1, 2, 3, divided by its mass. So our model will be basically these 6 equations, 2 for each of the moving masses. Let's do it. First, we'll start like this. The derivative of position 1 is speed 1, and the derivative of speed 1 will be, well, 1 over mass 1 times the resulting force, but I will directly write it in here to avoid introducing more letters in my model. The resulting force will be the sum of those from the springs the masses attached to plus the friction terms. So if we assume linear friction, the friction force will be a friction coefficient B times speed 1. We are now considering this part of the system. And then we have the fourth of the left spring. That will be a spring constant K times the length of the spring minus its natural length. And the length of the spring, if this were 0, the length of the spring will be P1 minus 0. So this will be P1. However, this is correct if we work in what we call absolute coordinates, but we are going to work in incremental coordinates. The origin of P1 will be the equilibrium position when the spring is, let's say, at its natural length. So when we think in these incremental coordinates or linearized models, then constants do not have increments and constants get out of our model. So instead of putting this in absolute coordinates, we will just write Kp1, and hence our model will be valid only if P1 is the increment with respect to the equilibrium position in which everything is stopped and springs exert no force. But okay, with that reference systems, why not? We choose it. So this is the left spring, and the right spring will have a force proportional to, again, the length of a spring, P2 minus P1 minus the natural length, if we were in absolute coordinates. But if we are in incremental coordinates, this constant disappears, and we write it like this. And then the only remaining thing is ensuring that the sign is correct in this equation. So if we think of the left spring and we assume positive means movement towards the right direction, rightwards movement, then the more positive is P1, the more negative, the more leftwards force this spring makes. So we should have a negative sign here in order to model that physical connection. A more positive P1 yields a more negative leftwise force of this spring. Now, if we think in the right spring, then if we move P1 towards the right direction, then this spring should push also in the left direction. If it's in equilibrium, then an increment of P1 in the positive direction should give an increment of the force in the negative direction of this spring in here. So the overall coefficient of P1 must be negative, and then as we have a negative sign here, then we do not need to change it. So this is the correct writing of the signs of the springs. So carrying out some operations, we can say that the spring equation is, this is a minus here, because also if P1 is positive, then friction goes in the negative direction. Then there we have the equation of the first mass in red. The other equations are very similar. The green mass, the derivative of its position is speed, and its acceleration will be 1 over mass 2, then, and again friction, a left spring making this force depending on P2 minus P1, and the right spring making a force depending on P3 minus P2. Again, a positive increment of P2 towards the right direction makes both spring increment is pushing in the leftwise direction if P2 moves to the right. So the coefficient of P2 in the equations must be negative. In here it's positive, so we need to change it. And in here it's negative, so we do not need to change it. So we sum up, and here we have the equation for the central mass, the green card. Last, it's more of the same thing. This left spring of the cyan mass will be something depending on P3 minus P2, and the rightmost spring, its increment of length, will depend on U minus P3. As movement of P3 in the positive direction makes both springs push a little more in the negative direction to oppose the movement, then sign of P3 must be negative, so we need a minus here, and in here we already have the correct sign, so we need no modifications. Then here we have the equation, which ends up like this. So this is finally the set of 6 equations, because, well, I mean, we have just rewritten those ones like here. So we have 6 equations and 6 unknowns, 3 positions, 3 velocities, and the model is complete, assuming that the input U, the signal here, is known for us. In fact, note that the normalized state space representation is something in the form like this. So if I name x as this vector, then I have already written my equations in normalized form, because these 6 derivatives at the left hand side of the equal sign is what this dx dt represents. This is 6-dimensional, and this fxu represents the 6 equations at the right hand side of the equal signs, in which only the letters in this vector appear plus input u. So this finishes the modeling. However, as this is a state space representation, but equations here are linear, only multiplication by constants and summations appear, then we can actually express this linear equation like here as a normalized linear state space representation, in which I have 2 constant matrices, A and B, that multiply states, these things, and input here. I leave it as an exercise, or, well, you can just watch the video that follows this one, in which we actually implement these equations in MATLAB and we carry out simulations. For the moment being, we leave it here. Thanks for watching.